Okay, guys, you ready? Okay, so what is this course? Anatomy, meaning structure, and physiology, meaning function. And both of them are like the two faces of one coin. They are dependent on each other, and the function is derived from the structure, and the structure is in the architecture of the function. So I gave you a very important parable, and that's how you have steel and steel. From one steel, you make a sharp knife, and from the other steel, you make a hammer. So structures are different, the function is going to be different. The cop does not have a wooden spoon, they have a weapon because their jobs is because they deal with crime. The chef in the kitchen does not have a weapon, the chef has the cooking utensils. So in the body, in the heart, you have these heart cells, the cardiac myocytes are full of cytoskeletal proteins. These are the proteins that push and propel the cells, and that is their function, to push the blood. Now, if I examine under the microscope the cardiac myocyte, does it resemble the neuron? Of course not. The neuron it looks like a computer. It has a nuclei. It has multiple nuclei. And the neuron, and this is what we're going to be doing in the course, and that is we're going to have a sensor. The sensor is going to detect a form of stress. Then it's going to use an input sensory, because it's a sensory, an input sensory signal. It's going to send it to a computer, an integration center, a computer for integration in and then based on the integration we came with an input, then we're going to have an output. We're going to have an output, and the output, if the input was sensory, then that means the output will be motor. And then the output is going to target an effector who will mediate the output. And then we're going to have to stop. We're going to have to stop sign. We're going to have to stop the response. Otherwise, we're going to move in the opposite direction. I'll talk more about that. This is what the neurons do. So that's why neurons have many nuclei. Have dendrites. The dendrites, they have terminals that receive sensation, and they have an outgoing motor peripheral nerves to the effectors in order to manifest our response. So there's no cytoskeletal proteins in the neuron, but there's a lot of cytoskeletal proteins in the cardiac myocyte. There is not a lot of nuclei in the cardiac myocyte. There's a lot of nuclei in the neuron. So, because the job of the neuron is to act like a computer, integrate an input signal and generate a motor output. That's its job. So it makes sense it has that kind of structure. Now, when we move on to a hepatocyte, the liver, that looks like a bow. You know, the bow and arrow. Okay, you know, you put the arrow here. This liver, it is made up of hepatocyte because glucose. So you have multiple glucoses attached together, and whenever our blood sugar drops down, we will see that hepatocytes will start to burst out sugar from the liver that acts like a storage site for glucose to supply our blood that needs sugar at times of a sugar drop. But the point is, the structure of the hepatocyte is different from the structure of the islet of Langerhans, and this is our pancreas. Our pancreas has many different enzymes, some of them to help the digestion, in our digestive system, and others are to help in the restoration of sugar homeostasis. So, and we're going to talk more about that. But for now, what am I trying to say? I'm trying to say that all of these cells, what is different? Their structure is different. Why? How actually? How did we end up with this kind of structure? So, whenever you want to understand the difference between two things, always begin with the similarities. If you're asked to tell what is the difference between a cardiac myocyte, a neuron, hepatocyte, an islet of Langerhans in the pancreas, what is the difference? Begin with the similarity. What is in common between all of them? They all have the same, excellent, excellent, excellent. They have the same DNA. They have the same exact copy of the DNA. They have identical, so the DNA, so the microsomes, they look like that. So I'm going to take one and spread it out. So if they all have the same DNA, how do they look different? If they all have the same DNA, how do they look different? It is because just because they have the same DNA, it does not mean it's all transcribed. It does not mean it's all active. So for example, the region in the DNA that when you transcribe it will give you the proteins necessary to give me a cardiac myocyte is region 1. Region 2, when you transcribe it, will give you the structure for a neuron. Region 3, when you transcribe it, for example, will give you a hepatocyte. Region 4 will give you the islet of Langerhans. So inside the cardiac myocyte, only region 1 is transcribed and everything else is inactive. So the active region of the chromosome is known as U chromosome or U chromatin. Chromatin. And the region that is inactive in the chromosome is known as heterochromatin. So, a cardiac myocyte is different from the rest because only the region that makes it a cardiac myocyte is euchromatin and the rest is heterochromatin. When you move on to the neuron, only the region that makes it a neuron is active while the rest is heterochromatin. So what I'm trying to say is, just because you are euchromatin in one type of cell, it does not mean you will be euchromatin on all of them. And just because you are heterochromatin in one type of cell, it does not mean you will be heterochromatin on all of them. So here we mix and match. We transcribe the region that will give us the structure that will help us do our function. And the rest is inactive. This is so important. Is this point clear? So we have a very important concept known as the central dogma of biology. What does the central dogma of biology say? The central dogma of biology says we have DNA. Once we transcribe it, once we do transcription, we get mRNA. And once we translate mRNA, we get proteins. Translate. When we translate mRNA, we get proteins. And our proteins, we have two types of proteins. Structural proteins for anatomy, and functional proteins for physiology. But this is the dogma. We begin with DNA. We transcribe it to get mRNA. Then we go to the ribosome. We translate it to get our desired protein. So the cardiac myocyte, it can never do its job without dynein. That's a very important dynein, myosin, actin. These are cytoskeletal mechanical proteins that help the cardiac myocyte push the blood, which is its job. So we go to the DNA, we transcribe the mRNA that when translated will give me my functional protein, will give my structure, because that's a structural protein. So it will give me my actin, myosin, and dynein. Is this point clear? Once I go to the other types of cells, for example, I now need to make an isolate of Langerhans. This isolate of Langerhans in the pancreas is the site where I have my pancreatic acini, and this acini can never be generated unless I go into the cell in the region where when I transcribe it, it will give me the mRNA that once translated will give me the proteins that will give me my acini, in which I'm going to be able to generate my isolate of Langerhans. So our DNA is a very long frame, but we target certain sequences to give us our identity, our anatomy and physiology as cells. So each cell is different, not because it has different DNA, but because the region that is transcribed, that is active, the euchromatin, is different from the other cell. Is this point clear? Now, this central dogma of biology, go tell that to HIV. Go tell HIV, listen, we can only get proteins, we can only get mRNA from DNA and protein from mRNA. That was supposed to be the central dogma of biology. But what does HIV do? HIV has a malignant, very dangerous enzyme known as reverse transcriptase. So reverse transcriptase, what it does is it takes the mRNA and goes the other way around. It reverses the transcription. So we're supposed to get transcription from DNA to mRNA, but HIV goes from mRNA back into DNA. So when HIV infects you, God forbid, when HIV infects you, what happens is it will hijack the machine. It has mRNA, it has no DNA. HIV has no DNA, it has mRNA. And it has this very dangerous reverse transcriptase. What it does is it's gonna use your cell, it's gonna convert its own mRNA into DNA. Then it's gonna use your enzymes to do the central dogma of biology. This is viral DNA. This is human DNA. And that is human mRNA. And that is human proteins. The virus now is going to use HIV reverse transcriptase to make viral DNA, then use human enzymes to convert viral DNA into viral mRNA, and then the viral mRNA is going to be translated into viral proteins, and then the virus is going to be able to make all the structural proteins it needs to survive and all the functional proteins it needs to survive, and that's how it's able to kill us. So the central dogma of biology is going in this direction, but it was hijacked by HIV, because now HIV has a special enzyme that can go the other way around and then hijack our machinery. Imagine HIV has no reverse transcriptase. It's going to be stuck in this region. So it can never make proteins because our ribosome can only accept the mRNA of our DNA. But what it does is it's going to convert its own viral mRNA to viral DNA, and then the viral DNA is going to be transcribed by the human DNA to give us viral DNA that is masked and decoyed as human mRNA, which will later be translated to give us proteins that are viral proteins. So do you now see how the HIV hijacks our own machinery? Okay, this is the central. So now we have talked about the central dogma of biology. In the central dogma of biology, we have our DNA. We have different regions. Just because the DNA is there, it is just so lazy and sleeping. It is not active, all of it. Some part is active. The part that is active is known as the euchromatin. Very good. And the part that is inactive is known as the heterochromatin. So what makes all of these cells different, although they all have the same identical DNA, is that, yeah, so they have different euchromatin. Yeah, so each one has the euchromatin that makes it unique. Okay, so we are done with all of these. Okay, so now structural proteins and functional proteins. How is that different? So structural proteins are proteins that have mechanical jobs, or they provide structural integrity for the body. Like your nails. See, these nails or the hair follicles, these are proteins, but they are there like a fence. Their job is to stand there to prevent the entry of infectious organisms, to prevent the entry of to prevent the entry of some dangerous substance. But their job is only structural. But that's not the only form of proteins that we have. We have functional proteins, and the hallmark of which is your hemoglobin. So what does hemoglobin do? Hemoglobin is very important because it can shuttle two different types of gases. Hemoglobin can shuttle two different types of. Okay, that's not good. Okay, so how can that be solved? So this is a lab. This is not supposed to be. Okay, lab. Okay, that wipes. Okay, so let's see. Okay, a little better. Okay, so hemoglobin, very important to understand what hemoglobin is. So hemoglobin is a functional protein. Hemoglobin is a functional protein. It has a function. And the function that it has is that it transports, it shuttles, transports, and moves our gases. So for example, that's my lung. So that's my lung. And that's my tissue. Dot represents a nucleus. So many cells give us tissue. Many cells give us tissue. Many tissues give us organs. Many organs give us organ systems. And many organ systems give us organism. Many organisms give us population. So, this is so important. In the lung, the partial pressure of oxygen, when you inhale, all the air went into your lungs. Do you think there is high partial pressure of oxygen in the lungs or low? When you inhale oxygen, think about it. There's no tricks here. There is no punishment. Just trust yourself. Think about it and answer. If you take a deep breath, all the air went into your lungs. Do you think there is high partial pressure or low partial pressure? There's high because you just took all the air in. So there is very high partial pressure in the lungs. What about the tissue? The tissue, you are running the marathon, you are running around the world, and this tissue is using oxidative phosphorylases. So you go to your job, you get the money. You come home, you buy your children the cereal, the stuff, the diaper, so they consume what you get. So this tissue is consuming through oxidative phosphorylation, is consuming oxygen. So it's using the oxygen. So do you think the partial pressure in the tissue here is low or high? Is very low. Is very low because this tissue is breathing aerobic respiration. Aerobic respiration. This tissue is breathing, so it's consuming all the air. So it needs to replenish this oxygen that it has used in oxidative phosphorylation. So you know the subway has two trips, downtown, uptown. So this trip is downtown. To carry, the hemoglobin will carry oxygen from the lungs downtown to the tissue that is suffocating and needs oxygen. And once it gets here, it's gonna diffuse all the and saturate all the oxygen in the tissue. But it's not over. This downtown. Now let's look at it in terms of carbon dioxide. This tissue, what do you think is the partial pressure of carbon dioxide in this tissue? Is it low or is it really high in this tissue that is toxic and is generating so much metabolic waste? And that is it. So what do you think? Very high in the tissue. What about in the lung? Do you think the carbon dioxide in the partial pressure of carbon dioxide in the lung, do you think it's high or low? Low. Very low because it's saturated with oxygen. So now you see the movement was from high to low, either way. So hemoglobin in one ride downtown, the subway going downtown, is all oxygen. So hemoglobin here, all the seats in the bus of hemoglobin, all of it, oxygen, 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 oxygen. Once it got here, now is empty because all the oxygen was unloaded. Now it will take back uptown, back to the lung. It will take carbon dioxide. And now when you look at the seats are now all full of carbon dioxide, carbon dioxide, carbon dioxide, carbon dioxide, carbon dioxide, carbon dioxide. So do you see how, so what do we learn from here? We learn from here that we move from an area of a high pressure to an area of a low pressure. This is another theme we will see again in fever. When it's hot, your brain is hot, and you put that, your mommy used to put that pad, that water, what is it called? Water rag? Okay, with the water rag. Why did they do that? Because your brain is hot and the water rag is cold, so heat is going to move from an area of very high heat to an area of less heat. So now this water rag is going to suck all the heat, pull all the heat from your brain. So the Motrin you take is going to slow the development of any more fever. But the fever you already had, what's going to make it go down? Is that pad. So many people don't know that. They just give the baby Motrin. They just give the elderly. They just give them that aspirin or Tylenol. I'm sorry, Tylenol. Then they forget to. You know these $5 fans. You know the little fans that spin. So if somebody has fever, you have to put that rag and you have to put that spinning fan. So, and you give them also the Motrin and the Tylenol. So the Tylenol and Motrin will stop the propagation or the making of any more fever to be removed with this fan that's making you a little bit cold. So heat is going to flow from an area of high heat to an area of low heat. Gases move from an area of high partial pressure to area of low partial pressure. Here, carbon dioxide, high partial pressure of carbon dioxide to area of low partial pressure of carbon dioxide. That's how hemoglobin works. Now, hemoglobin is part of the blood. So the blood, all of it is not hemoglobin. Hemoglobin is about 45% of our blood. That's the red blood cells, the erythrocytes. That's 45%. Our blood has other stuff in it, nutrients. So this tissue here is not only hungry for oxygen, for oxidative phosphorylation. It's also hungry for lipids, steak, lipids, fats, and cholesterol. These types of, like, let's say you had a meal, steak, and pasta. So pasta is carbohydrates. And then you eat proteins with all of that. So we need separate systems. So when you eat, your digestive system is going to separate them from each other. So the job of the digestive system, obviously, is to break them down into small chunks, then to separate them. So lipids are going to be on one side, carbohydrates, you come over this side, you're not lipids, and then protein, you move over to the other side. You're not lipids or carbohydrates. Then we deliver them to the tissue. The tissue will receive them and send them to the cell. Then the cell is gonna shuttle them in different pathways to get ATP. So if you are a lipid, fat, or cholesterol, you're gonna be shuttled into a biochemical pathway. This is called metabolism. Metabolism. This metabolism is going to we're going to shuttle it into a pathway of metabolism known as beta oxidation. If you eat carbohydrates, you're going to shuttle the carbohydrates into a pathway known as glycolysis. Glycolysis to get ATP. And then proteins are going to be shuttled into protein catabolism pathway to get ATP. So we got ATP, all right. We got it in the end, but with different systems. So we do not have one system for everybody. We don't just have that one system where no matter what you eat, you just shuttle the same micromolecules there and you get ATP. No, you have to separate and you have to shuttle and shunt all of the different nutrients in the right direction. So your blood is supplying oxygen for your blood is supplying 2 pluses and removing 1 minus. Your blood is giving 2 good things and removing 1 bad thing. The first good thing it's removing is oxygen. The second bad thing it's giving is the nutrients for ATP, nutrients. And the bad thing it's removing is carbon dioxide. It's removing carbon dioxide and it's removing metabolic waste, garbage, buildup, poison buildup. So all of these metabolic processes, beta oxidation, glycolysis, protein catabolism, they all have byproducts. They make garbage. So that garbage starts to accumulating in the tissue. Then the blood comes in to remove all of that. So the blood gives in 2 plus, removes 1 minus. Gives in 2 plus oxygen and nutrients, removes carbon dioxide, metabolic waste. So that's how people get stroke. Because when it comes to stroke, what happened in stroke? That's the tissue waiting for oxygen, waiting for +1 oxygen, +2 nutrients, and the removal of metabolic waste. But the patient's blood vessels are clogged. So the blood is not moving 100%. So 100% is on this side, but only 20% is passing. That means only 20% of the tissue is getting oxygen, nutrients, and metabolic waste removal. The rest is gonna die. And that's how when they die, so your brain is like a computer, we said. You know, the computer has one region, that's the mouse, there's the monitor, there's the central processing unit, there's a keyboard, and it has different jobs inside. So your brain has a center for hearing, a center for walking, a center for vision, and a center for emotion. So it depends on which part did not get its oxygen, which part did not get its nutrients, which part did not have the metabolic waste removal, that part is going to die. When it dies, what it used to do. So some people who have stroke, they have hearing problems. Some people who have stroke, they have vision problems. Some people who have stroke, they have one side of the body that is paralyzed. Why? Because they have different regions in their brains that had the stroke, and that region, so for example, the stroke that I had affected the region responsible of vision. That's why I cannot see no more. The stroke that another patient had is affecting the region. I didn't have a stroke, I'm just saying that. And I hope I don't. No. Okay, and then another patient had another stroke, but their stroke, they can see fine. So don't think if a patient had a stroke, they're supposed to have the same symptoms. No, the brain is like the universe. Actually, we know more about the universe than our own brain. The brain is more intricate and complex than the universe. But my point is, why is blood important? Because it provides oxygen, provides nutrients, and removes carbon dioxide. But we have gradient, the concept of gradient. What is gradient? From more to less, from more hot to less hot, from more electricity to less electricity, from more amount, if there is 500 molecules of glucose on one side and 20 on the other side, then the 500 are going to move until they equilibrate. So if you have 100 molecules of glucose on one side, 0 on the other, then you open the permeability chamber. What's going to happen is you're going to have 50-50. They're gonna move, they're gonna diffuse from where? From an area where you had a lot of glucose. That's always how it is. From an area of a lot of glucose, a lot of heat, a lot of molecules, to the area where you have less. But that does not mean we cannot have a molecule like sodium, potassium, ATPase that we paid the energy currency of the cell ATP to do the opposite. So usually we go from a lot to little. But you will learn that there is a molecule, an enzyme known as the sodium potassium ATPase. It does the other way around. It takes stuff from a little bit, throws it back to where there's a lot. So we're gonna learn more about that. Okay. So the diffusion is very important. It's actually one of our. So are we done with hemoglobin? Are we done with how hemoglobin has two trips, downtown and uptown? One trip, but no matter whether it's downtown or uptown, we always move from high partial pressure to low partial pressure. So in one trip, we go from an area of a high partial pressure for oxygen, the lungs, to deliver it to an area of low partial pressure of oxygen, the tissue. Then when the seats are empty, then we take carbon dioxide from an area of a high partial pressure of carbon dioxide to give it back to an area of a low partial pressure of carbon dioxide, and that would be the lungs. Okay, and okay, so now let us talk about this concept of diffusion. So we have learned that we move either uphill or downhill. We move uphill or downhill. So we'll have a big break at 4. So we did an hour now. Then we'll do an hour and a half. Then you'll have a big break when we move there, and we do like a half hour. So at 4:30, you guys can have like a very big break, and then come back till we finish up. Okay? All right. So now let's talk about diffusion. So when it comes to diffusion, we said that this is a concept that is dependent on gradient. So in gradient, there has to be disparity. There has to be disparity. One side has to have more and one side has to have less. So let's say that I have a beaker, and this beaker has an impermeable membrane in the middle, and I have two sides, A and B. On side A, I have 100 molecules of glucose. On side B, I have 0. On side B, I have 0. Then I have made a semi-permeable or differentially permeable membrane. what is going to be the result of the experiment? You will see that glucose is going to move from A to B, and the movement is going to stop when you have equilibrium. Equilibrium. And equilibrium will be when I have 50 glucose molecules and 50 glucose molecules equal on both sides. So that's how diffusion happens. With water, same thing with water. If I had on one side, I have A and B again. I have side A and B. And both of them, I fill them equally with water. Okay? And I have placed, this used to be deionized water. There's no ions here. But now I add sodium and chloride to one side. And I add 500 millimoles of sodium chloride on one side. And on this side, I have, let me say that I have 400 millimoles. Okay? And on this side, I have 200 millimoles of sodium chloride. What's going to happen is water is going to start moving from an area of a more water concentration to an area of less water. So it's going to move to dilute. It's not going to be concerned with the 200. The water is going to move from this direction to this direction to dilute the 400. So water moves from an area of a high water concentration, low solute concentration, 200, to an area of a low water concentration and high solute concentration. So what is called osmosis. Osmosis is a special type of diffusion where water diffuses from area of higher water concentration to area of lower water concentration. An area of a high water concentration and low solute concentration to an area of low water concentration and high solute concentration to dilute the solution. Okay, so that's a type of diffusion known as passive diffusion. It just happens naturally. Passive diffusion happens naturally. It does not need a motor. It does not need ATP. It happens on because it relies on kinetic energy. Kinetic energy. Where kinetic energy, Ke equals half mv squared. So, so what happens here, what drives, what powers? So anyways, if there's a movement, no movement will happen for no reason. I need a form of energy that powers the movement, even if it's a passive diffusion. Even if it's passive movement, I need some power, some energy. So what is the power that is powering the passive movement of water from an area of a high water concentration to an area of a lower water concentration, or glucose from an area of a high glucose, or sodium chloride from an area of high sodium chloride concentration to an area of low glucose? What is downhill? Even if we're moving downhill, what is powering that movement? I just mentioned it. Kinetic energy. So when you have all of these molecules bumping to each other and it's too crowded there, then they're going to start to migrate where there's less. Think of it as you have 100 people in one corner of the room, and then you make the room a lot wider, then they're going to start to disperse. So the kinetic energy of them bumping to each other is going to lead them to move from an area of a high, dense concentration to an area of a low concentration, to separate equally. Now, just because it's passive, there is another problem. Sometimes in the cell, Like let's say this is the cell membrane. The cell membrane in the core is made up of lipids. And we know that like dissolve like. Salt dissolves in water because water is polar and salt is polar. And oil dissolves in detergent. But detergent doesn't dissolve in water, and water does not dissolve in oil. So likes dissolves like. Birds of the same feather flock together. So here, if you have cholesterol, it can pass easy. But glucose, even though there is a lot of glucose and a little bit of glucose inside the cell, even though that there is kinetic energy, even though there is diffusion gradient from high to low, it cannot cross. So it needs a carrier protein that is plucked here, to help and facilitate its movement through this lipid. Otherwise, it cannot cross the lipid. So this is called facilitated because we need a facilitator. We need a facilitator that facilitates the movement of glucose down concentration gradient through the cell because the cell has a hydrophobic core. Same thing with water. Water cannot cross the lipid. That's why we have aquaporins. What are these aquaporins? These are channels that allow for the entry of water. So just because you have the potential, just because you have the gradient to flow down concentration gradient, it does not mean you have access. So you need to ensure you have the access. That's why in our body, if we need glucose inside the cell, we need to plug in membrane channels to allow the passage of glucose, known as GLUTs, G-L-U-T, GLUTs, glucose transporters. So that's what insulin does. So in insulin, when there is so much glucose outside the cell, when insulin is secreted, it's gonna plug so many channels. These channels now are gonna allow for the passage of glucose from the blood into the cell, and that's gonna drop the sugar levels in the blood that was hyperglycemic. Is gonna make it euglycemic. We're gonna talk more about that. But now do you see that we need a gradient to diffuse? So one of the movements is diffusion, and that is moving from one area of a higher concentration of what? Higher concentration of gas, oxygen, or higher concentration of molecules, or higher concentration of heat, an area that is more hot. So if you touch the stove, heat is not going to go from your body into the stove. The heat is going to come from the stove into your body because your stove is more hot. So heat is going to always flow from an area of a higher heat to an area of a lower heat. Or an area of, also we do this with charges. So sometimes if you put sodium positively charged, you put 500 sodium ions out here and 100 sodium ions inside. Sodium is going to move from this side to this side. So 500 plus 100, that's 600. They're going to equilibrate at 300 on both sides. What about chloride? If you put Cl minus, you put 500 millimolars of Cl minus, and there is on this side 100 millimolars of Cl minus, then the movement is going to be from this side to this side until you end up with equilibrium, 300 millimolars of chloride on one side, 300 millimolars of chloride on one side. So that shows you there's also electric potential. From more electronegative, we flow to where there is less electronegative, or from more electropositive to where there is less electropositive. So you just need a gradient. Whenever you have more to less, the movement is going to be diffusion. So, and diffusion is passive movement. If the membrane is permeable, it can allow you to cross like a lipid membrane, then you can cross so smoothly from an area of a higher. We still need to be from high to low. But if there is no access, then we utilize facilitated diffusion, which is still diffusion, still passive, still from an area of a higher concentration to an area of a lower concentration. But the only difference is that it needs a facilitator. It needs a protein carrier that mediates this passage. So that's very important. So that is passive. The opposite of passive diffusion is active. So active diffusion, what does active diffusion mean? Active diffusion, I'm sorry, there is never active diffusion. Active transport, because remember we said diffusion is always passive and from an area of a higher concentration to an area of a lower concentration. We have active transport. In active transport, we start to utilize ATP. So for example, there is more sodium outside, let's say this is the cell membrane. There is more sodium outside the cell. It is known, it is measured, more sodium outside and less sodium inside. So the sodium potassium ATPase, what it does is sodium naturally diffuses from an area of a higher concentration to an area of a lower concentration. Sodium potassium ATPase moves sodium from an area of a low concentration to an area of a high concentration. That's the opposite. So that's why it needs ATP. That's why active transport requires ATP. And that is known as the primary active transport. Primary active transport. Primary is when you use ATP. So this sodium potassium ATPase is working the other way around. Inside the cell, there is a lot of potassium, inside, and a lot of sodium outside. So potassium naturally passively diffuses out, and sodium naturally passively diffuses in. The sodium potassium ATPase, whatever that diffused in, she will take 3 sodiums from inside to the outside against the gradient. So now we're going uphill. Before it was downhill. Sodium from a lot of sodium to a little bit of sodium. Potassium from where there's a lot of potassium to where there's a little bit of potassium. But the sodium potassium ATPase does the opposite. It takes the sodium that has walked in and send it right back where there was a lot. Do you see the problem? Do you see what I'm trying to say now? Okay. So what did we say diffusion does? Diffusion allows for the movement of sodium from an area of a high sodium concentration to an area of a low sodium concentration. You have 500 sodiums there, 100 sodium here, then you open the gates, they're going to equilibrate, where the 500 are going to start dispersing here until you have equal amounts, 300 on this side, 300 on that side. That's passive diffusion. Active transport is when we go against it. So, yeah. So now, instead of going from 500 to 100, those 100 who came in from the 500 side to the 100, the sodium potassium ATPase would throw them back out. And it's two things. It's sodium and potassium. And you got to ask yourself, why does it got to do that though? Why is it doing that? Why is the sodium potassium ATPase doing that anyways? Why is it using ATP to help throw things uphill against their gradient? We're going to learn that in the nervous system because that is how we prepare for the action potential. So the action potential propagates when the sodium flows in to depolarize the membrane. But in order to do that, we have to ensure that there is no equilibrium. And that's what sodium potassium ATPase does. It makes sure that it's always gradient so that when the action potential comes in, they move in. But if it allows sodium to move in from outside to inside, you will have equal amounts on both sides. So no action potential can be generated now. It's like now we are dead. So the dead people, they have equilibrium between outside and inside. electrolytic, electrolyte equilibrium. But the sodium potassium ATPase is important because it makes sure there's always a gradient so that when an electric stimulation comes in from your brain, it's able to be mediated through the depolarization. We'll talk more about that in the right time. But for now, you need to understand that we move either uphill or downhill. Uphill is the natural movement, but it doesn't mean it's the better movement because in some situations we need active transport, in other situations we need passive transport. And we're going to talk about the different kinds of situations. But for now, all you need to know is familiarize yourself that we move through a gradient, pressure gradient, from high pressure to low pressure, thermal gradient, from high heat to low heat, electric gradient, from more positive to less positive, from more negative to less negative. Um, Also, molecular diffusion from an area of a lot of molecules to an area of less molecules. So that's just what we need to know for now. Okay, are we clear with that? Any questions? Okay, all right. So now we're done with diffusion. Now let us shift to the sensor. So now I said to you, always going to be discussing how to restore, how to restore Okay, so in the traffic light we have green, red, and yellow. So green is the region where we belong. That's the healthy. So if you are green, you are healthy in the right region. Okay, and yellow is you are getting ready. You are in the adaptation zone. So you are not yet sick, but you are not healthy. You are trying to. So and lastly, you have red. That is when you cross the line and you enter into the red zone. That is the line of damage beyond salvage. Okay, so green is where we belong, known as homeostasis. Okay, what happens is our body senses with a sensor. It senses a stress. Then it will send an input signal. This input signal will be integrated by an integration center, like a computer. Okay, and that integration will lead to an output, to an effector. Then we're going to stop or terminate the response. So let's see, what does that mean. So our body has multiple homeostatic variables. We talked already about temperature, like thermia. So if there is excessive temperature, if it's dangerous, if it's too hot, we call that hyperthermia. We call that hyperthermia. Temperature is too hot. If it's too cold, we call that hypothermia. So we don't want hyper or hypo. What do we want? We want euthermia. We do not want, for calcium, hypercalcemia. Too much calcium, too much calcium. And we do not want hypocalcemia. We want eucalcemia. For sugar, we do not want hyperglycemia or hypoglycemia. What do we want? Euglycemia. For blood pressure, we do not want hypertension. We do not want hypotension. What do we want? Eutension. So now we're going to learn how does our body repair all these variables. So let's begin with the thermia. I already mentioned that one. So when it's too hot, let's say we are at 37 degrees Celsius. That's healthy homeostasis. That's green. If this green homeostasis, if this healthy 37 degrees Celsius goes up to 39 degrees Celsius, it's too hot. What's going to happen? A sensor is going to detect that there is a hyperthermia. As the first step number one. That's step one. The sensor is going to detect that there is hyperthermia. Then the sensor is going to send an input signal to your hypothalamus in your brain, in the brain stem, in the base of your brain, telling the brain to an input sensory signal that, hey, there is hyperthermia. The hypothalamus, the computer, will integrate. It will integration that there is hyperthermia, and we need to negative feedback. So if it's too hot, we need to make things cold. We cannot do positive feedback. If it's too hot, you make it even more hot. That's even more hyperthermia. So now we're hot, so we repair hyperthermia with positive feedback or negative feedback. Negative feedback. If you're going so fast with the brake, with the accelerator, do you press on the accelerator more or the brake? You press on the brake. So you do negative feedback. So the integration is going to negative feedback. It's going to do a negative feedback, and the output is going to send to the effector and then the negative feedback is going to cause an effector. The first effector is the blood vessels. So when it is so hot, your blood vessel diameter is going to increase. That's the first response. That's the first effector. The effector is the one who responds to the integration. So the blood vessels are going to become really wide. So what is the usefulness of your blood vessels becoming so wide? What's going to happen is when they're so wide, blood is going to be shunted to the peripheries. So now your blood is going to be shunted from the core to the outer skin. And the outer skin is close to the weather. So now, who's more hot? The weather or your body? Your body. So we're suffering from hyperthermia where? Are we suffering from hyperthermia inside our body or in the air? Inside our body. So this hyperthermia, guys, this hyperthermia here, what does it describe? Does it describe an increase in the temperature of our body or the temperature of the weather? Who cares about the weather? This is our homeostasis. That's our body. So when there is hyper something, it's our body's hyper, not the weather. So now, what's going to happen is, it is so hot, blood is shunted to the periphery. What's going to happen now? The heat is going to flow from our blood vessels into the air. So now we're going to dissipate the heat from our body by shunting it, by making the blood vessels wide and shunting it into the into the periphery so that the heat in the blood can be exchanged and leaves. Because remember, we said we move from high to low. So now our body temperature is so high, it's going to move from our body to the weather. And that's how we're going to lose the heat. Make sense? Okay, that's one mechanism. If it's not working, there's an additional mechanism, sweating. So your body is going to perspire. It's going to secrete water. Water is very special substance. It's the most miraculous substance. Water has so many properties that makes it the most important substance for life. Water is a versatile solvent. Water can dissolve anything. Not anything, obviously. It cannot dissolve lipids, we say that. But nobody dissolves more things than water. I mean, water, compared to any other substance, it has the most capacity to... If there's any substance, who's more likely to dissolve it? It's water. So water is a versatile solvent. That's one property. The second property is water has very high specific heat capacity. So water does not evaporate easily. So we need that. That's perfect for us. Because if our sweat is a lot of water, it's going to take a lot of sun rays in order to evaporate that sweat. So now the sweat is going to be our number one line sunscreen. You know, people, they put sunscreen. That's actually the second sunscreen. The first sunscreen is your sweat. So your sweat is like a capsule. It encapsulates you and is interacting with the sun on your behalf. The sweat says, you can't get to the body, you have to get through me first. And obviously, the sun is not going to get through the sweat because the sweat is full of water, and water has very high specific heat capacity. That's why your sweat does not evaporate in the sun. When you stop sweating, it means you have cooled, but it doesn't mean that the sun has evaporated it. So it really fights the sunlight, the sun rays. So that's how. And then when you secrete the sweat, what happens is, so let's say that's your skin and that's sweat. So sweat is deflecting the sunlight and absorbing the sunlight and evaporating. And from inside, the heat is being absorbed by sweat. So sweat is absorbing heat on both directions, from the sun and from inside your body. And that's how we get rid of the heat. And then what happens is our temperature goes down from hyperthermia into homeostatic range, 35 degrees Celsius, and then we stop. Because imagine we have returned to homeostasis. Imagine we return to homeostasis and you keep on sweating. So now you're going to get even colder. And you're going to move from homeostasis to hypothermia. So you need to stop. Many people think this goes on and on. Input signal, integration, effector, sweating, and vasodilation forever. No, you got to stop. Because you're going to reverse things around now. When you get here, you need to stop here. Otherwise, you're going to move even more down. So I talked about hyperthermia. What about hypothermia? Now it's the opposite. Now it's too cold. It's not too hot anymore. It's now too cold. So now it's 30 degrees Celsius. What happens in 30 degrees Celsius? What happens now? The same steps again. A sensor is going to detect what? Hyperthermia or hypothermia? Hypothermia. It's going to send an input signal that is a sensory input signal to the integration center, telling the integration center there is a hyper or hypothermia. Hypothermia. Then the output signal is a motor. Output signal is going to go and is going to your blood vessels. First of all, it's going to go to your blood vessels. It's going to go to your blood vessels. What is it going to do to the blood vessels? If we were hot, it will dilate the blood vessels. If we are cold, what do you think it's going to do to the blood vessel? Excellent. It's going to constrict the blood vessel to prevent loss of heat. I'm already cold. You want me to vasodilate? So now the little bit of heat that I already have is now going to leave. So now I'm going to constrict the blood vessel. That's the first line. Doesn't end here. There is another one. The same way hyperthermia has two ways: vasodilation and sweating, perspiration. The being too cold has two ways too, and that is vasoconstriction and shivering. Excellent. It's called shivering thermogenesis. So it will send electrical stimulation that causes your skeletal muscles to move, and the skeletal muscles, when they shake and when they move, they're going to convert mechanical energy into ATP, and then that ATP is going to be harvested like burning, like Bunsen burner. It's going to be used as chemical fuel to warm you up. And then when the shivering helps us go up from hypothermia to homeostasis, we gotta what? Stop. Otherwise, we're gonna go up into hyperthermia. So that's an example of the variable temperature. There's another variable, pH. Our pH is supposed to be between 7.35 to 7.45. More than 7.45, that is alkalosis, very dangerous. Below 7.35, that is acidosis, very dangerous. So your body has a buffer system. It has a buffer system that helps it. And when you're respiratory, you will see that in anatomy and physiology too. In the respiration, you're gonna expel out carbon dioxide. It's gonna elevate the pH. In the urine, you're gonna urinate a lot of carbon dioxide. It's gonna also help out. And also there is a lot of buffers, protein buffers, amino acids that they're gonna help you restore the pH. So that's another variable, pH. It can go up and down, but we need it to be fixed. There's another variable, calcium. So hypercalcemia, if there is so much calcium, hypercalcemia, we sense calcium, there will be an input signal, sensory signal that will be integrated. There will be extra calcium. Who's going to sense that? The integration center now is going to be the parathyroid gland, which is a gland in the back of the thyroid gland. The thyroid gland is like a bow tie in front of the neck. So the parathyroid gland is right behind it. It's going to realize that there is so much calcium. So what it's going to do is it's going to send a hormone known as calcitonin. And calcitonin is going to start taking calcium from the blood and dump it into the bone. The bone is a big mountain full of minerals, phosphate, and calcium. What about the opposite? If you don't have hypercalcemia, why are we so concerned and so worried about having too much calcium? I mean, it's too much calcium. Too much calcium is very dangerous. Too much calcium can turn from off into an on, very dangerous enzymes. So you know, the people who drink alcohol, drinking alcohol, when alcohol goes inside your body, it's going to be metabolized into acetaldehyde and then into reactive oxidative species. This reactive oxidative species is going to damage the liver. That's why there is alcoholic liver disease. So that reactive oxidative species causes inflammation. This calcium, extra calcium, is going to turn on in the pancreas some very dangerous proteolytic metalloproteinases, degradative enzymes that will end up auto-digesting and auto-destroying the pancreas, because the calcium is like a switch that turns things on. They were off. They will always be off, except when you have too much calcium, then they're going to be turned on to destroy your own pancreas. So we need to repair that. Hypercalcemia cannot be left alone. It has to be repaired with calcitonin. What about the opposite? What if you have too little calcium? Well, that's dangerous too, because your heartbeat is dependent on calcium for the depolarization of and the action potential. If you don't have enough calcium, you cannot have your heart beating, you cannot pump blood, blood cannot get to the tissue, no oxygen, no nutrients, no removal of metabolic waste, then that's going to lead to the death of the tissue. So we need to repair that too. And we repair it with, obviously, the opposite hormone, who is parathyroid hormone. The parathyroid hormone is going to go into the blood, degrade the bone, and get powder from the, the bone is like a mountain of calcium. Is going to degrade it into powder and start to supply the blood with the calcium that was low and bring it up to homeostasis. So we have different variables, but This is the process. Negative feedback, sensing, input, sensory signal, integration, output, and effector. Okay, do we only have negative feedback? What about positive feedback? Do we ever need that? Oh yeah. What about when the baby is born? So when the baby is born in labor, the baby push with his head in the cervix. So when you stretch the cervix, electrical stimulation is going to be sensed and sent up to the brain, and the brain is going to respond by sending extra contractions to expel and push the baby out the cervix. So the more the baby push with the head, the more the uterine, the uterus is going to push it out. So the baby push, uterine push. Baby pushes, uterine push until the baby comes out. The same thing with suckling the milk. So when the baby suckles the mom's nipple, when the baby is suckling the mom's nipple, it's gonna stimulate and pull the nipple. There's mechanoreceptors on the nipple. These mechanoreceptors, when they are stretched, electrical stimulation goes to the brain and leads to more milk coming out. So the more milk the baby suckles, the more milk comes out from the gland, from the duct. The more the baby push, the more is the uterine pushes. The more the baby suckles, the more the duct pushes. So that shows you that positive feedback is not always bad. It's dangerous if it's used with these guys. Here, hypercalcemia, hypocalcemia is dangerous with them. But we also need it in other aspects, like in labor. It's very important to have um, positive feedback. So these are very important two situations. Who is the hormone who mediates that positive feedback? Oxytocin. Oxytocin. So when the baby pushes in the cervix, oxytocin is released. It makes the uterus push the baby out. Oxytocin. Suckling the milk, the same one. Oxytocin again. So when the baby suckles the breast milk, the oxytocin is secreted and more milk is ejected from the milk duct. Oxytocin when you are being born, and oxytocin when you are suckling the breast milk. So that's an example of positive feedback helping us out. So it's not as bad as we always think, as we thought. Any questions? Any questions? I am tired. Okay, can I drink Gatorade? I mean, can I drink? I should drink Gatorade, but I'm drinking Canada Dry. Okay, any questions so far? I'm looking forward to questions. I am looking forward to questions. Are there any questions? Okay, so should I ask questions? Okay, no questions. Okay, so how about I ask questions? Yes, please. Okay. Yeah, you said it good. Aerobic respiration. Yeah, so that's how we breathe. We utilize oxygen. That's what depletes the oxygen. So the processes, these biochemical pathways, that we utilize them in order to convert our nutrition to useful ATP. Why do we need ATP? We need ATP to power the enzymes. So hemoglobin is an enzyme. There are many enzymes that mediate this metabolism. Do you think glycolysis is one step? No, it's like 10 steps. It has all enzymes, and all of them need ATP. So when we don't have ATP, the sodium potassium ATPase I mentioned to you that's working uphill is not going to work because she needs ATP. If it doesn't work, no depolarization, no action potential, heart stops. Other biochemical pathways dependent on enzymes. Enzymes, if it wasn't for them, the reaction is supposed to take place in 1,000 years. But they accelerate the reaction by making smaller the activation energy barrier. I'll tell you more about that once the ginger ale is done. But for now do we know why ATP? Do we know why ATP is important? We are trying to get ATP to power our enzymes because our enzymes, they cannot do their job except that ATP except that except that we have except that the ATP is there. Any questions? 15 minutes. What have I forgotten to talk about? There's something I forgot to talk about. What is it? Any questions? Okay, so we will do the lab over there, I guess. Any questions? No questions. Yes, please. Okay, so there are different effectors for different loops, for different systems. So when it came to the thermogenesis, so when it was too hot, who was the effector? The first effector, the blood vessels. It was too hot. The effector were the blood vessels. They dilated, dilated to remove heat. The second effector was the sweat glands. They secreted sweat. Okay? That was one effector. On the other case, when it's shivering thermogenesis, the first effector was blood vessels. They constricted. The second effector was, what was the second effector? The skeletal muscles. Who shivered? The skeleton. So the action was shivering, but who mediated the shivering? It was the skeletal muscles. They are the ones shivering. Okay? Now, when it was with calcium, when there was so much calcium, who was the effector? The effector were the so the thyroid was the integrator. Very good. Thyroid is not the thyroid, the parathyroid gland. They integrated. There is a fluctuation in calcium, and now we need to secrete calcitonin in order to deplete calcium from the blood, because there's too much calcium in the blood, and dump it like clay, like mud on the surface of the dump calcium from the blood on the bone. Very good. So here the effector were these cells who take the calcium from the blood into the bone. They are known as osteoblast. Osteoblast. The other types of cells, when there is a depletion, there is too little calcium now in the blood. We need to make more calcium. So what happens now, the effector are known as osteoclast. Osteoclast. They go and they start digging this mountain of calcium salt to liberate calcium from bone into the blood. Very good. So effectors are different. We're going to go into all of them. Don't worry. You will know by the end of Anatomy and Physiology 1 and 2 every single effector out there, every single homeostatic variable, and how we replace it. And then after that, we're going to move into reproduction. We're going to be studying the evolution. We're going to be next semester, if you're with me, we're going to be studying the evolution. We're going to be studying how, because biology is not just homeostasis. You ensure the survival of the organism. We move on to the next stage, which is the survival of the population. Okay? I mean, people who live on top of the mountain, it's not fun up there. It's a little bit of oxygen. So how do they survive? Their body makes extra red blood cells, so they have more capacity to take more oxygen. So you see how the body adapts? So your body is going to adapt in order to for the population to survive. So there's always survival. The survival of who? If we want to survive the organism, that's homeostasis. If we want to survive the population, then that's a whole field known as the reproduction. Okay? Okay, so before we go into the lab, the concept of stress. So all of this is stress. I talked about calcemia. Let me just talk about sugar. So now, another variable is glycemia. Glycemia. So glycemia is blood sugar. Too much sugar, that is hyperglycemia. Too little sugar, that is hypoglycemia. We don't want hyperglycemia. We don't want hypoglycemia. We want you what? Glycemia. Good. You too. Euglycemia. Very good. Excellent, excellent, excellent. So now let's look at how do we get to euglycemia from hyperglycemia. A sensory signal is going to detect what? Hyperglycemia or hypoglycemia? Hyperglycemia. A sensory input signal is going to relay that there is an increase in blood sugar, hyperglycemia, to the integration center, who is the pancreas at this time. It's not the parathyroid no more. It's not the hypothalamus. It is the pancreas. The pancreas now is going to respond with an output signal to the pancreas acini, who will secrete, they will be the effector who will secrete insulin. Insulin is gonna pluck so many GLUT. What's the GLUT? What's the GLUT? GLUT is the glucose transporter. Because remember, we said glucose cannot go through the lipid membrane. It is a facilitator. So I call it facilitated diffusion. So this GLUT, the glucose transporter, is gonna help. So now that's blood. That's blood where there is a lot of glucose, hyperglycemia. And that's the inside of the cell where there is a little bit. So now they're going to start taking in glucose, in glucose, in glucose. So now glycemia is going to drop down from hyperglycemia into euglycemia. Then we're going to stop secreting insulin, and these GLUT channels are going to shut down, and then we're going to remain at homeostasis. So we used insulin to repair hyperglycemia into euglycemia. What about the opposite? If there's too low sugar, hypoglycemia. If there's too low of sugar, a sensory signal is going to detect that there's a drop of sugar. So we're going to have hypoglycemia. We're going to send a sensory input of hypoglycemia. Sensory input is going to send it into the integration center. In that case, it is your pancreas, who will send a motor effector response to the effector sending insulin. What is it going to send now? Glucagon. Who said that? Somebody over there. Excellent, 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 excellent. So glucagon is going to go and liberate glycogen belt with so much glucose and liberate glycogen into the blood, and that's going to elevate glucose. So now we have restored hypoglycemia. So you see there are two different systems, but we're always trying to restore and repair glycemia. We're always trying to restore and repair glycemia. Are we clear? Okay. For the last thing I want to say now is the concept of stress. So the concept of stress is a very important concept because stress is the beginning of disease. So the fire starts with a spark. The fire starts with a spark. The fire starts with a spark. So disease starts with a stress. And the stress goes on and on, not repaired, and that leads in the end to disease. Okay, so we begin. So now when we look at patients suffering from chronic inflammation, we must understand that we did not begin with chronic inflammation. So we have chronic inflammation. That's the last thing. We began with stress up here. And we have different types of stress. We have physical agents such as hyperthermia, hypothermia. That's an example of a physical agent. What's an example of a chemical agent? A chemical agent is a Corrosive agent, like a detergent that you pour on your hand that causes an abrasion or a laceration in your arm. That's a chemical agent, chemical stress. What about infectious disease, infectious microbes? A parasite, a virus, a bacteria, a worm, fungi. These infectious organisms are a form of stress. Infectious, infectious organisms. What about ultraviolet radiation? That's also a type of stress. So that shows you every single day we are the subject of constant stress. But our body is able to respond and adapt. Yellow is adaptation. But there are factors that lead things to get worse. So stress can exacerbate to cell injury. And cell injury is going to lead to cell death. And cell death is going to lead to necrosis. And necrosis is going to lead to inflammation, acute inflammation. Then acute inflammation is going to lead to chronic inflammation. So what causes stress to go to cell injury, damage? And what leads from cell injury to cell death? Three things. The onset, the duration, and the intensity of stress. I mean, imagine the stress was so intense. Like the hyperglycemia wasn't 200 milligrams per deciliter. It was 2,000 milligrams per deciliter. I mean, how intense is that? Or the hyperthermia. We're not dealing with 40 degrees Celsius, 400 degrees Celsius. I mean, that's intense. So that leads to stress going down this road. So intensity can push stress and make it win against your body. Also the onset. If it happens so quickly, your body didn't get enough time to respond. And lastly, the duration. Even if you have a little small stress that lingers on week, 3 weeks, a month, 2 months, 6 months, a year, then that's gonna now develop into a disease. So these three factors push things in the negative direction and make them win against your body. Once you cross this line, green is where you need to be, yellow is where adaptation, your body's putting up a good fight. But if onset was sudden, quick, duration was really long, intensity was severe, you cross this line, no coming back. It's called the line of damage beyond salvage. You cannot save it. You cannot salvage it no more. It's damage beyond salvage. Then you move on to chronic inflammation, and healing is going to be healing by fiber, scar tissue formation. Things are going to get really bad after that. After the point of damage beyond salvage. Okay, so let's go. I mean, maybe we can stay in this room. It's hot in here. It's getting hot in here. Okay, let's go. Let's go to the other room. Who knows? Maybe the other room is more hyperthermia than here. Okay, all right, guys. We're going to 309. 309. We're gonna be in there really quickly for a half hour. We do the labs, then you have your break. 307, I meant. Sorry, 307.